Hello, my name is Bendish. I work for New Instruments in the UK, part of Ametec's Materials Analysis Division. I'm the product manager for the Astrum, our glow discharge mass spectrometer. In this webinar, I will be introducing the Astrum, looking at some of its features, a brief description of Gdms, and what analysis can be done, an example of results that can be achieved with the technique. Glow discharge mass spectrometry is today well accepted as the industry standard for analysis of high purity materials. The first generation instruments, called VG9000s, were deployed back in 1985, and many are still in use today and considered the golden standard. The Astrum was designed to be the natural successor of the VG9000 in terms of both design and capabilities. With GDMS, the analysis takes place directly in the solid material, with minimal to no sample preparation required. The instrumentation can measure from matrix down to sub-ppb levels in one scan, and almost all elements from the periodic table can be quantified this way. First, a simple introduction to how the GDMS works. If you look up glow discharge on the internet, a recurrent definition would sound a little bit like: glow discharge is a plasma formed by applying a voltage between two electrodes in a low pressure gas environment. Let's consider a flat piece of conducting material as one electrode containing M atoms or molecules that we want to analyze, and on the other side the GD source acting as a second electrode. We introduce a low flow of argon in the system. After applying a voltage difference, the conditions in the source are such that the argon atoms break down into ions and electrons. Under the electric field present, the argon ions are then directed towards our sample, where they impact with the surface layer and release some material. This is effectively called sputtering and is how our material is sampled. The atoms are then colliding with other electrons and argon ions present and ionized as well. Finally, the flow inside the cells makes the plume of ions of interest to exit the cell towards the mass spectrometer. At all times, both sputtering and ionization are continuous processes in the source, providing a constant flow of ions to the mass spectrometer. The mass spectrometer is designed to separate and detect the ions formed in the source. Basically, the plume of ions is extracted, accelerated, and focused to form a thin ion beam. The beam then enters a magnetic field where ions are separated based on their mass, and only one mass at a time is reaching the detector for quantification. By scanning the magnet, it is then possible to sequentially measure each isotope separately with a concentration more or less proportional to the size of the signal detected. This is the basic working of GDMS. Next is what can be analyzed with GDMS. The main application for the technique is the analysis of conductive material, such as high purity aluminium, titanium, copper, or tantalum, for example, as well as alloys of different sorts, such as nickel, aluminium, or copper-based alloys, wires and foils, but also conductive powders, usually as long as they are compactable. On a side note, it is also important to mention that non-conductors, such as metal oxides or ceramics, can be analyzed with GDMS. In this case, we use a sacrificial electrode made of a high-purity material to sustain the glow discharge. The non-conductor is placed onto the electrode or exposed, allowing for the non-conducting material to be sputtered and ionized as well. Now onto typical data from the GDMS. Here we have a mass scan from lithium to uranium of a high-purity copper sample, where data has been recorded for matrix element and all traces. If we focus on one part of the results, we can see that they are displaying a few ppb to sub-ppb values. Overall, the results achieved show many elements with ppb or less detection limits and purity of 4, 5, and 6N are easily achieved. As an example, the analysis of a 6N copper sample will take about 2 hours, and that includes handling, tuning the instrument, and multiple replicate measurements. In this section, we would like to highlight the main benefits of using the Astrum Gdms for high purity material analysis. First, let's talk about sample and sample preparation. One key factor is that Gdms analysis is run directly in the solid. Therefore, there is no digestion or dilution step involved, as would be the convention for solution ICP-MS analysis. In cases the sample is actually difficult to digest and using a cocktail of chemicals, labware, and handling steps are prone to introduce contamination in the sample and result in poor data. The sputtering process seen earlier also, in time, cleans the surface of the sample to expose the core material. As for the shape of the sample, the Astrum allows for flat and pin shapes to be run. A flat sample is typically about 11 to 35 mm long and wide, and from a few millimeter or so to about 20 mm in depth. A pin sample is 2.5 by 2.5 or less, and about 22 to 25 mm long. Other shapes have been run on the Astrum, so please take both these descriptions as usual samples but not exclusive. Now on to the source design. The Astrum source is based on what is called low-flow, glow-discharge technology. It means the amount of gas used is very, very low, resulting in a very stable glow and sputtering over time. The source is also cooled at liquid nitrogen temperature, which is about -185 degrees C, which is essential for samples that are thermally unstable. Finally, most of the parts requiring to be changed after the recommended usage period from the sample holder and the GD source can be cleaned and reused many times without any problem. Overall, the level of consumables required for an analysis is very small. Regarding detection limits, as mentioned earlier, a Gdms analysis takes place directly in the solid. We can see that in most of the cases, the instrument is actually measuring nothing or only a few random background counts. This allows for extremely low detection limits to be calculated and reported, without the need to apply a dilution factor correction to the instrument data, as opposed to solution ICP-MS. And last but not least, reproducibility of data. For quality control, reproducibility of data is paramount, and relying on good instrumental data is a very sought-after aspect of daily analysis. Here we have a set of results for bismuth in a certified nickel alloy sample. The RSD on this set is less than 10%, but the characteristics of this set are very interesting, as the set includes data from 7 different Astrum instruments obtained by 5 operators, being application scientists and engineers at the factory. There are over 70 analyses made over about 5 years from the first to the last data point. This truly shows the robustness of the Astrum and, as mentioned earlier, the low-flow technology for repeated analysis and achieving the same result again and again. To summarize, Gdms is the industry standard for the analysis of high-purity materials. The direct analysis in the solid allows for excellent detection limits and minimal to no sample preparation. The technique can measure from matrix to sub-ppb levels and almost all elements from the periodic table. If you are interested and would like to find out what the Astrum can do for you, please get in touch and we will discuss further. Please also keep in mind that full training on the instrumentation and its inner workings, as well as data processing, can be provided. Thank you for your attention.